Hello, in this section I'm going to look at matrix multiplication. So you've already looked at different types of operations on matrices such as addition, subtraction, and even looked at different types of matrices like square, row, column, etc. Now here I start with a simple problem where I have like k times a matrix. So basically this defines what we call scalar multiplication. So we have that this would be that you would have k times a, then you have k times b, and then k times c, and then k times d. Now basically all that says is that you can take any constant k. So if you have that a is m by n, basically whenever we multiply the constant k times a, you have that this is still an m by n matrix, but if you want to get specific in terms of the entries, well, basically what's happening is that the entry k is being multiplied, or the constant k is being multiplied by the entry ai sub j. So that means that you just have to multiply every single entry by k, essentially. So like, for example, if we had 2 multiplied by 3, 3, 6, and then let's say that we have 5. Well, I know that this would equal to 6, 12, 10, and then 8, and then that would be it. Now, one thing that you can look at, though, as it relates to matrix multiplication or scalar multiplication, is that you can actually look at, if you take a matrix like A and you multiply it by a scalar, and then let's say that you have minus 3 but times B. This basically is possible only if A and B both have the same dimensions. So in that case, that's one thing that you'll have to look at as it relates to combinations. So like, for example, if you knew that A was the matrix, like for example, like 1, 3, 2, -1, and then you knew that B, uh, you knew that B was equal to, let's say like 0, 5, -1, and 6, then you know that basically 2 times A would be, well, that would be 2, 6, 4, -2, and then you know that minus 3, B, would be equal to 0, -15, +3, and then -18. But the whole idea is that you would just add these two. So like you just combine. So when you do that, you're just basically just adding. So like 2 plus 0 is 2, 6 minus 15 is -9, 4 plus 3 is 7, and then -2 minus 18 is -20, and then that's it. Okay, so that means that we have that linear combinations of matrices definitely does work in this case. But the other thing of which that we can look at, for example, is how do we multiply a matrix? So let's say that you have that A is M by P, and let's say that you have that B is P by N. So whenever I form the matrix multiplication, I have A times B But the thing that you should look at essentially is the dimensions. That's where it matters. So we know that A is m by p. So this is our A. But then we also know that B is p by n. So what we need here is that the outer dimensions, they're going to determine the size. But what's most important is that these two are the same. So we have to have that these two have to be the same. Okay, so in this case, this is going to yield a matrix that you can call C, but that new matrix is basically going to be of dimensions m by n. Okay, but this doesn't really answer the whole thing as to how do you get matrix multiplication? How do you get from A times B to C is m by n? So the way to do that is to think of it this way. If you take a random row of, let's say, like A, and you call it R1, R2, and then let's say that this is going to be, yes, this is going to be RP. Okay, so we took a random row of matrix A, and we're just calling it row 1, or R1, R2, and so on. But let's say that we take a column of B. So if we take a column of B, well, we're going to do it like this. We'll say that we have C1, C2, all the way down to, let's see, we'll have to say CP. Okay, so what I'm doing is I'm just taking a random row of A and a random column of B, but they have to be technically the same corresponding row in this case. Like if you have that you're looking at row 2, well, I guess it doesn't really matter technically, but it should correspond, if that makes sense. So what you would have to do here is say that this is going to be row 1, or let's say R1 times C1 plus R2 times C2 plus, you repeat this process until you've multiplied every corresponding entry with each other. Now, this may seem a bit, kind of arbitrary or even just like really complicated. So the best way to kind of visualize it is to think of like this. If you have a row, like for example, like 1, 2, 3, and then 4, well, there has to be as many columns, or in this case, yeah, there has to be as many rows for the corresponding column. So like for example, if you have the entries 2, 4, 5, and 6, basically the multiplication that's going to happen is going to be 2 times 1 plus 4 times 2 plus 5 times 3 plus 6 times 4. So what this does is it gives us 2 plus 8 plus 15 plus 24, of which from there we can add this to be 40, let's see, 39. Okay, so this will be 49. Okay, so essentially we just have to repeat this whole like row by column method. So this is our row, and here this is going to be our column. I'll just write it over here. Okay, now it's best that you see this in an example. So for example, so let's say that we have the following matrix. Let's say that we have 3, 4, 5, negative 1, and we're going to multiply this by, okay, so we're going to multiply this by 1, 2, 0, -3. Let's do like this, -3. And then we have 4, and then we have 0. Okay, now the main thing that you need to realize is that the dimensions, they must match in the inner. So we have that this is a 2 by 2, this is a 2 by 3, but notice that definitely they are the same, but that the output is going to be a 2 by 3. So how do we do this? Well, it has to be done by row by column. So the way that I normally do this is that I just kind of work off of, saying that, okay, well, I have the first row that I need to take care of, and I need to multiply it by each corresponding column. So that's going to be 3 times 1 plus 4 times 2. Now, that basically took care of the first entry, but then I have to repeat that process again. So like I would have 3 times 0 plus 4 times -3. And then I repeat that process again. So I have 3 times 4 plus 4 times 0. But basically, I have to repeat that process all over again as it relates to the next bottom entries. So we have that we're going to take 5 and we're going to multiply this by the first row. So we have 5 and then we have 1 plus -1 times 2. Now notice that when I multiplied this second row by this first column, that we just have the same exact numbers. So I'd like to think of it like, I could have just said, well, I already know that I'm going to use row 2, and it's 5, -1, and I just need to fill in these values. That is one way to look at it. If not, then you just use the definition as needed. So you have -1 times 0. Now, all that you need to do from here is just really simplify. So you have that this equals to 3 plus 8, which is 11. You have 5 minus 2, which is 3. You have, that's going to be -12, and then that's going to be +3. But then we also have that this is going to be +12, and then we have 20. Okay, so we see that our resulting matrix is this one right here, which is also a 2 by 3, but that's not really a surprise. Now, let's go ahead and try where we try to find the product of A times B. So let's say that A is the following matrix, 2, 5, -4, 3. And then let's say that B is equal to 4, -3, 1, and 2. Okay, so we want to find the product of these two matrices. So the way that we can do this is by saying that, well, we know that you're going to take 2, 5, -4, 3, and you're going to multiply this by the other matrix, which is 4, -3, 1, and 2. So, of course, this is a 2 by 2, this is a 2 by 2, so we should expect that this is going to be a 2 by 2. But remember that if the dimensions over here did not match, then there wouldn't be anything to do. So the next step is that we just need to figure out what the entries are. So I have 2 times 4 plus 5 times 1. Now, if you kind of have a highlighter, what you could probably do is just say that, you have this row and then you multiply it by that column and then repeat the whole process all over again. So I have 2 times -3, and then I have plus 5 times 2. That's for the top row entries. So you repeat this process all over again, where you take the bottom row and you multiply by 4, 1. So I mentioned that you can either look at it like you're just filling in the parentheses with the values, or you can just apply the definition, because you know that you're going to multiply the bottom row times column 1 and the bottom row times column 2. Okay, so that's going to be -3 plus 3 times 2. Okay, so this gives us the following. It gives us that, okay, so 8 plus 5 is 13. -16 plus 3 is -13. 10 minus 6 is 4. And then you have 12 plus 6, which is 18. So this is our matrix that we resulted in, A times B. Now, if I was to reverse the process though, like for whatever reason, if I wanted to find B times A, okay, so if I take B times A, the main thing that you should realize is that when you multiply this through, that you're going to get 20 for the first entry, because that's 8 plus 12. And then you're going to get 20 minus 6, or no, wait, 20 minus 9, which is 11. Then you're going to get 2 minus 8, which is -6. And then you're going to get 5 plus 6, which is 11. Now, notice that basically this is just telling me the following. Let me just check my work. So 4 -3 multiplied by this is going to be 8 plus 12, which is 20. Okay, and then I have 20 minus 9, which is 11. And then I have 2 minus 8, which is -6. Then I have 5 plus 6, which is 11. Okay, so basically this is telling me that A times B is not equal to B times A. And that's actually pretty useful as it relates to saying that matrix multiplication it does not commute. Okay, now there are some certain properties that we do have for matrices. So for example, we have that if I take A times B plus C, well, it's the same thing as A times B plus A times C. Okay, but then I also have that if I take A and I multiply it by B and C, this is the same thing as A times B times C. Now, the thing that's wrong with this is that basically you have to assume that the dimensions do correspond, because otherwise, if they didn't, then there really wouldn't be anything to do. So here we just have to assume that the dimensions do match, and that's where it gets kind of funny. So that's why I didn't mention what A, B, and C are. They're just going to be matrices in a way that the multiplication does work out. Now, one of the last few things that I want to look at is, for example, identity matrices. So like, for example, if I have that A is m by n, well, if I multiply by the left side by A, okay, so if I multiply the left side of A by I sub m, basically that's going to give me the matrix A. But if I multiply A and I multiply it by I sub n, that's going to be equal to a. Recall that basically I sub n, or I sub m, is basically just a matrix with a series of ones and zeros. And then you have 0. Then you have 0. Okay, so basically you have that this dimension has like ones, or this n by n matrix has ones and zeros. Now, for example, if I wanted to look at A is equal to, let's say like, um, you have 3, 4, 6, 7, 1, 2. Basically, you would have to multiply this matrix on the left side. You would have to multiply it by I2, which is 1, 0, 0, 1. But then, if you want to get the same thing on the right side, when you multiply it, you would have to multiply it by I3, which is 1, 0, 0, 0, 1, 0, 0, 0, 1. Now, I will say that basically you do have that there. It's not really a coincidence that you have that this matrix or these matrices look very similar to how you were reducing a system of equations. But do know that, yeah, that the identity matrix is basically just corresponding to however many equations and unknowns there are in this case. So let's say, for example, that you have this problem. So we want to find the values x, y, z, and w such that you have 3, 7, 2, 5, x, y, z, and w equals to 1, 0, 0, 1. Okay, so this is actually an interesting problem because it requires that you know matrix multiplication, but not only that, but it requires that you know matrix equality. So, for example, when we multiply this through, you're going to get the following. You're going to get that 3x plus 7z, and then you're going to get 2x plus 5z, and then you're going to get 3y plus 7w, and then you're going to get 2, 5, 2y plus 5w. Okay, but this has to be equal to 1, 0, 0, 1. So all that this means is that essentially you have several equations now. You have that 3x plus 7z equals to 1, and then you have 2x plus 5z equals to 0, but then you also have another set of equations. You have 3y plus 7w equals to 0, and then you have 2y plus 5w equals to 1. Now, this is actually kind of interesting because basically we could actually solve for both. Uh, we could solve for both, essentially. Okay, so really all that means is that you would have to solve these following augmented matrices. So you would have 3, 2, 5, 7, 1, 0, and then you would have 3, 2, 7, 5, and then this is going to be 0, 1. Now, interestingly enough, what we could probably do instead is just solve, well, yeah, we can probably just solve each of these individually, because we know that, for example, if you subtract row 1 and row 2, that gives you a new row 1. So this is going to be, okay, so this is going to be 1, 2, 1, and then this is 2, 5, and 0. Okay, now I could probably just do -2 times row 1 plus row 2 to give us a new row 2. But what does this give you? It gives you that essentially you have 1, 2, 1, and then you have 0, 1, and then you have a -2. Okay, well, the next step that you would need to do is you would need to basically just take -2 times row 2 plus row 1 to give you a new row 1. But that gives you the following. It gives you that you end up with the matrix 1, 0, 0, 1, and then you get 5, -2. Now, interestingly enough, it gave us basically um, x and z. So we know that basically x and z are equal to 5 and -2 respectively. But notice this. If you kind of do the same thing over here, like where you reduce this, basically you're going to get that when you reduce it, you end up with -7 and +3. So that tells you that essentially we have the answers. We have that x equals to 5, that y equals to -7, z is equal to -2, and then w is equal to 3. Okay, so in this case, we have that the matrix that we're looking for is the following. It's 5, -2, -7, and then 3. Now, you'll notice that if you multiply these two times each other, like if you multiply the matrix that we were looking at, 3, 2, 7, 5, and you multiply it by 5, -2, -7, and 3, you'll notice that basically that this equals to 1, 0, 0, 1, and that's it. But interestingly enough, it is possible that you might hmm, you might be able to show that if you interchange these two, that it might still give you the same thing, but that's for you to try to figure out. Okay, now, last but not least, the things of which that you can probably look at. The other thing of which that you can look at is suppose that you have a matrix. So like let's say that you want to find x and y. So suppose that you have a matrix like 3, 4, -2, 5, and then let's say that you have a matrix x and y, and that this equals to 18 and 11. Well, note that basically when you multiply this through, you get 3x plus 4y, and then you get -2x plus 5y, and then notice that basically that this is equal to, let's just do this, this is equal to 18 and 11. Now, matrix equality states that basically that these are both the same, the entries. So essentially you would have that 3x plus 4y equals to 18, and then you have -2x plus 5y is equal to right, 11. Now, notice that basically that this is just a systems of equations. So in a sense, if we would have started here, we could have, and we still would have gotten the same exact result that you're like, oh, well, can't I just solve that just by using a systems of equations like with the Gauss-Jordan method? And you have -2, and you have 5. You augment it to 18 and 11. Now, what you can probably do here is just go ahead and find what is the values of which gives you the solution. So, you could always say, well, row 1 plus row 2, that'll give me a new row 1. Why? Because I need to get this to be a 1. So that'll be 1, 9, 29, and then I have -2, 5, and 11. But notice that if you want to basically get, let's see, 23, 29. So notice that we could probably just take 2 times row 1 plus row 2 to give us a new row 2. So what that'll do is it'll tell us that we have the following. We have 1, 0, 9, 18 is 23, and then that's going to be 58, which is, let's see, that should be 69. So we have that that's going to be 29. Now notice that I can actually solve for the bottom entry by taking 1 over 23, multiply that by row 2, and that gives us a new row 2. So in this case, we have that reduces down to 1009, or sorry, 1901, and then that's going to be 29, and then that's going to be 3. Okay, so the next thing that you can probably do is just multiply the bottom row by -9 times row 2 plus row 1, and that's going to give you a new row 1. Technically, I would have probably just used back substitution because it's a lot faster, but since I got to this point, I might as well just finish it. So I have that'll be 2, because you have 29 minus 27 is just 2. So that tells you that the value is equal to 2, and that y is equal to 3. So that means that the solution is 2 comma 3. Now, notice that if you would have that one thing that you could have done, for instance, well, and sorry that this is a little not straight, but notice that if you would have said that A was equal to the matrix 3, 4, -2, and 5, and then let's say that you had that x was equal to little x and y, and then let's say that B was equal to the following equation, or matrix 18 and 11. Now, basically, we know that we took A and we multiplied it by x, and that this was equal to B. So if this is true, then that means that technically I can solve for x by multiplying by the inverse on both sides. So I have that x is equal to A inverse multiplied by B, which means that this is the solution. Now, I'm using this term inverse because that's exactly what it is. But in the calculator, if you actually do like where you have A divided by B, or B divided by A, it's going to recognize what you mean. But in the event that you have that this matrix is what we call non-singular, so like if we have that if A is, actually we'll say dependent, then basically you have that the solution may not exist, or many. But if many solutions exist, then in that case, that means that, yeah, you have infinitely many solutions. Okay, so these are basically the cases that might exist as it relates to solving a matrix just by doing a to the -1, multiplying it by b, and then saying that that's your x. Okay. You might get a message back that says that the matrix is singular, but basically that means that the matrix cannot be used. Okay, so to kind of like wrap that up, essentially, if you happen to have that scenario where you tried to use this method, that would just mean that you have to go back and see like what happened, which means that you can use Gauss-Jordan, substitution method, elimination method, echelon method, and so on. So unfortunately, it means that this quick method does not necessarily work at all times.